So in this lesson, we want to dive deeper into the study of polynomial functions. Let's get started with the conjugate zeros theorem, and this word here should be the word zeros. There, I changed it. The conjugate zeros theorem. It says basically if p of x is a polynomial function, and you know that a plus bi is a zero of the function, then its conjugate a minus bi is also a zero. All right, so let's see if we can use this theorem to our benefit here. And this word here keeps changing there. This word keeps... Okay, sorry about that. I don't know why this word keeps changing from zeros to something weird. But all right, anyway, here is an example. Find a cubic polynomial function, so that's degree 3, in standard form having zeros 3 and 2 plus I. So listen, they've already given us 2 of the 3 zeros, right? 2 of the 3 zeros. In order to write out what this function is, we're going to need to know all 3 zeros. All 3. They gave us 2, so there's 1 missing. When we're done with that part, then we're going to move to part B, which says find a polynomial function satisfying the conditions of part A above, with the additional requirement that p of negative 2 is equal to 4, meaning if you were to plug in negative 2 into your function for x, your output is 4. We'll handle the second part, after we find the function from part A, and then we can tackle the second part. So here we go. I'm going to use the conjugate zeros theorem here to say that if 2 plus I is a 0, then I know 2 minus I must also be a 0. And that's what the conjugate zeros theorem says. So them giving me this 0 implies that 2 minus I is also a 0. So we have all 3 zeros. What I'm going to do now is I'm going to write out my function in factored form now that I have all my zeros. All right, so I have my function. I called it p of x. And if 3 is a 0, then x minus 3 is a factor. If 2 plus I is a 0, then x minus 2 plus I is a factor. And if 2 minus I is a 0, then x minus 2 minus I is a factor. What I'm going to do is I'm going to simplify this factor, and then I will then multiply all of this out so I can get this polynomial in standard form like they've asked. Okay, so I'm going to get x minus 3, and then this will be x minus 2 minus I, just distributing there. And this one will be x minus 2 plus I. Okay? What I'm going to do next is multiply. And I'm going to multiply these two trinomials first, and then I'll multiply by the binomial last. Okay, I just wanted to show you steps here so that I make sure that you're with me. What I did was I distributed x here. X times x is x squared. X times negative 2 is negative 2x. And then x times negative I is negative ix. So that's what I put here. And then when I distributed the negative 2, I just stacked up like terms. And when I distributed the I stacked up like terms. So when I distributed this negative 2, negative 2 times x is negative 2x. So that's this one right here, that term. And then when I distribute negative 2 to negative 2, I get positive 4, so that's what I wrote here. And then when I distributed negative 2 to negative I get positive 2i, so that's this term. And then I went ahead and distributed I times x is ix, that's here. And then I times negative 2 is negative 2i. And then I times negative I is negative I squared. So I like to multiply this way just so that I can see, like this term and that term are canceling, and this term and this term are canceling. Don't forget that I squared is equal to negative 1. So this will be minus, watch your signs, it'll be minus negative 1. So this will turn into a positive 1. I'm going to write that down right here. So I'm just going to cross that out and say that's a positive 1. Okay, everybody? Because it's minus negative 1. So that 1 and that 4 there make a 5. So then this turns out to be, I know it's a little sloppy, I apologize. X minus 3 is the first factor, and then you have x squared. Combining like terms, you get minus 4x, and then you get plus 5. So all we have to do now to write this in standard form is distribute. I'll distribute an x, and then I'll distribute the negative 3. I did the same thing. I stacked up like terms here as I distributed x and distributed -3. I get x cubed minus 7x squared plus 17x minus 15. This is my final answer for the function. Let me write it out. So p of x is equal to x cubed minus 7x squared plus 17x minus 15. Now this is the function that they were looking for, and it is written in standard form. It's not factored form, but standard form, okay? Now, we want to move on to the next part. The next part, I'll remind us, says that we need to find the function that satisfies part A. So this is the function that they're looking for, but with the additional requirement that when you plug in -2, you get 4. So here it is in words, okay? So what we're going to do is we are going to insert or substitute -2 for x, and we need the output to be 4. Now what I'm going to do before I get started is I'm going to rewrite the function from part A like this. Now multiplying the function by some real number a, like I am doing now. Let me finish writing here. Okay, there. Now you must understand that multiplying the polynomial function by a non-zero constant, right, a, will give us the same function having the same zeros, the same zeros being 3, 2 plus I, and 2 minus I. Multiplying by some non-zero constant will not change that, okay? So what we're going to do, so this is a more general form here. What we're going to do is we're going to replace p of x with 4 is what they wanted, right? So they need the output to be 4. Oh, excuse me, sorry. I think I have the wrong pen. There we go. We need the output to be 4, and we're going to be plugging in -2 for your x values. So if I can just show, if I can squeeze it all in here, I think I can. There we go. So basically, it's at this point just isolating a, like what does that coefficient need to be in order for p of -2 to really be 4. So you're going to see me simplify all of this and then solve for a, isolate a. All right, so I'm on my way. I'm simplifying this, and it's leading me to a is equal to -4/85. So this is what that leading coefficient should be in order to satisfy the requirement. So I'm going to now write my function. Actually, so I don't mean to make you dizzy there. I'm going to write my function. Let me change the color here. So p of x then is equal to -4/85 and then times x cubed minus 7x squared plus 17x, excuse me, minus 15, okay? So now this is the function. Now hear me well. This is the function such that the zeros are 3, 2 plus I, and 2 minus I from part A, right? And now it's also the function such that when you plug in -4, excuse me, when you plug in -2, you get 4, okay? I want to simplify this just a little bit though. I'm going to distribute this -4/85. So then the function can be written as -4/85 x cubed plus 28/85 x squared, right? Yeah, that's right. And then minus, let's see, this simplifies here. 17 divides into 85 exactly 5 times. So this should be -4/5, I believe, x, like that. And then 15 and 85 share a common factor of 5. So when you divide 15 by 5, you get 3. 4 times 3 is 15. 4 times 3 is 12, excuse me. And let's see. When you divide 85 by 5, you get 17. So this should be 17. This is just simplifying using fractions. So this is the final answer. Again, this is the function, the cubic polynomial. Look at degree 3. Cubic polynomial whose zeros are 3, 2 plus I and 2 minus I, and p of negative 2 will give you 4. If you plug in negative 2 into this function, you're going to get 4 as an output. All right, two very important theorems here. One is the fundamental theorem of algebra. Every function defined by a polynomial of degree 1 or more has at least one complex zeros. Now, you have to remember that complex zeros include real zeros, okay? So a real zero is a complex zero. So please remember that. Okay, now we must also understand that a function can have only real zeros, or it can have only, non-real complex zeros, or it can have a mixture of both, okay, a combination of both. The other theorem is the number of zeros theorem. So a function defined by a polynomial of degree n has at most n distinct or unique complex zeros. So, like, for example, a cubic degree 3 polynomial function will have at most 3 complex zeros. A quartic or degree 4 polynomial function will have at most 4 distinct complex zeros, okay? All right, we're going to use these theorems to answer a couple more questions. Here's a fun example. Find all complex zeros of this quartic polynomial function, given that 1 minus I is a 0. Okay, so the first thing we're going to do is I'm going to use synthetic division with this 0 here, because my idea is this. There are a total of, at most, 4 zeros here, right, everybody? At most, 4 zeros. I'm going to have to find all 4. Well, 1's already given, so I just need to find 3 more. 1 minus I is a 0. By the conjugate zeros theorem, 1 plus I is also a 0, so that's 2 out of the 4 zeros. So I just need to find the last 2. Okay, so let me write down what I said so far. 1 minus I is a 0. That implies that 1 plus I is also a 0. So that's 2 out of the 4 zeros. So in order to find the remaining 2 zeros, I'm going to use synthetic division for each of these zeros. And after doing synthetic division 2 times, I will go from a quartic polynomial down to a quadratic. And I know how to solve a quadratic function, a quadratic equation, in order to find the last 2 zeros. So that's my thought process, okay? So here we go. I went ahead and used synthetic division on 1 minus I. Now, when you do this process, remember that when you add complex numbers, you're kind of like adding like terms, right? So negative 7 plus 1 is a negative 6, right? And then you just bring down the negative I. Also, don't forget that this is multiplication. So 1 minus I times negative 6 minus I gives you negative 7 plus I. So you may want to remember that when you multiply these two complex numbers, don't forget that I squared is negative 1. Getting this 0 here as a remainder does not surprise us because we already knew 1 minus I is a 0. So we expected to get a 0 here as a remainder. What I'm going to do now is go through this process again, but I'm going to use this 0 now, 1 plus I, and I'll be using these coefficients. Now remember, these are the coefficients of a cubic polynomial because you started out with something degree 4, so now this is degree 3. Okay, so I'm going to set this up. I'm going to use 1 plus I this time around, and maybe if I use another color, just pop out a little better. So I'm going to use 1 plus I, the other 0, and I'm going to be using these coefficients here of the resulting cubic polynomial. Okay, all right, let's go for it. All right, now this is important. After I do this synthetic division, now we're at something degree 2. These are the coefficients of a degree 2 polynomial. So please allow me to write this as 1x squared minus 5x plus 6. Now, if I solve this quadratic equation, And I could use the quadratic formula, I can complete the square, or I can just factor this. I always prefer to factor if I can. And then just use a zero product principle here, or rule. I find that the remaining two zeros are actually real numbers. They are 3 and 2. So to answer the question, they said find all complex zeros of this polynomial function. They are 1 plus or minus I, right? One of those was given, by the way. And then we have 2 and 3. Notice that there are a total of 4 complex zeros here, 2 of them being imaginary or just complex, and the other 2 being real numbers. Now, they're all complex. You can say all of them are complex, but these are real numbered zeros, and these are non-real numbered zeros. So here we have an example that says find a polynomial function with real coefficients of least possible degree, that's important, having a 0 of 2, so 2 is a 0, of multiplicity 3, a 0 of 0 of multiplicity 2, and a 0i of single multiplicity. The first thing I would like to say is because I is a 0, the conjugate zeros theorem says that negative I is also a 0. Okay, so let's count how many zeros we have now. 1, 2, 3, 4, 5, 6, 7. If you notice, I counted each zero according to its multiplicity. In other words, 2 is a 0 of multiplicity 3, so you must count it 3 times. So that's 1, 2, 3, 4, 5, because it's multiplicity 2, 6, and 7. So the least possible degree here is going to be 7. I'm going to write that out. So degree, I'm going to put DEG, okay? The least possible degree this function can be is degree 7. Now what I can do here using the factor theorem is I can actually write my function out in factored form. What should we call it? How about P? P of x is equal to. Now, one of your zeros is 0, multiplicity 2. So that factor is going to be x squared, okay? Another 0 is 2. That means your factor is x minus 2. Now the power that's on this factor must be 3 because it says multiplicity 3. I'm going to put a power of 3 there. And then let's see, I, that means your factor is x minus I. And the other one is negative I. So it'll be x minus negative I. Or if you'd like, just x plus I. So what I'm going to do at this point is I am going to multiply all of this out. So I'm going to distribute, and I'm going to get my function in standard form. All right, so just I'm going to show you step by step here. So I wrote this as x plus I. I'm going to go ahead and distribute these right now. First, the order in which you multiply does not matter because of the commutative property of multiplication. Says that the order of the factors does not change your product. So anyway, you get x squared here, and then you're going to get plus 1. Now, don't forget that negative I times I is negative I squared, but that should give you positive 1 if you're careful about your signs, okay? What we can do is we can distribute this. We're going to need to know what x minus 2 quantity cubed is, so let's actually expand that. Okay, so far I have expanded x minus 2 cubed, that's right here. And then what I did next is I distributed x squared plus 1 to this 4-term polynomial. So that's all of this. And now I'm ready to distribute x squared. So I get, I think my final answer here, I get x to the 7th minus 6x to the 6th plus 13x to the 5th power minus 14x to the 4th plus 12x cubed minus 8x squared. That is my final answer. This is a degree 7 polynomial function. It's the polynomial of least degree, having all of the zeros that we had mentioned in the very beginning. The zeros, I can still see them, 0, 2, I and negative I. All right, last example for this little lesson here. We want to sketch the graph of this quintic degree 5 polynomial function. They wrote this function both in standard form for us and factored form, so I'm really grateful for both of these. I'm grateful for both because in standard form, I can get I can pick off two things right away that are really important for the graph. Number one, I can see that the leading term is negative 2x to the 5th power. That's my leading term. Because the leading coefficient is negative and the power is odd, I do know the end behavior is up forever on the left and down forever on the right. That's my end behavior. Also, standard form gives me my y-intercept, negative 6. So I'm going to write that down. I have a y-intercept 0, comma, negative 96. So those two things were given to me, practically given to me, because of standard form. So I'm very grateful for standard form. And then I'm grateful for factored form because this gives me all of my zeros. Factored form does. Standard form does not. Factored form does give me my zeros. So if x plus 4 is a factor, that means negative 4 is a 0. So let me write this out here for us. I'm going to write out the word zeros. Okay, so we have negative, bear with me. Okay, cool. We have negative 4 as a 0, and I'm going to put capital M for multiplicity, multiplicity 2. I do know it's multiplicity 2 because of that power that's on that factor. Another 0 is negative 3. If x plus 3 is the factor, then negative 3 is the 0, and that has single multiplicity. Finally, positive 1 is a 0 of multiplicity 2. Now, what we must remember is that whenever a 0 has even multiplicity, like negative 4 and 1, that even multiplicity implies that these two are touch points or bounce points on the graph of our function. In other words, the graph will not cross the x-axis at negative 4 and 1. It'll just touch it. So I call them bounce points or touch points. Our textbook calls them, I believe they call them touch points, but I'm just going to go ahead and use the word bounce points if you don't mind. Okay, so this is going to be a bounce point. I'll put BP for bounce point, and this one's going to be a bounce point as well. Any 0 that has odd multiplicity will be a cross point. So I'll just put CP for cross point. Okay, so that's going to be very important. With my end behavior, with my y-intercept, and all of my x-intercepts, and their multiplicity, I can sketch the graph of the function. So let me do that now. I can do that down here. And remember, it's just a sketch, okay, everybody? So, of course, we're doing this by hand. So here we go. Let me see if I can do this for us here. There's my x-axis, okay? And here's my y-axis. I have a 0 of, let's see, negative 1, 2, 3, negative 4 there, negative 3, and then I have another 0 at 1. Okay, now I'm going to scale my y-axis very differently. I'm going to say this is negative 96. Okay, so bear with me there. All right, so my zeros are negative 4, negative 3, and positive 1. Now remember, the zeros of a polynomial function are the x-intercepts of its graph. Also the y-intercept of negative 96. Now let us not forget the end behavior of the graph. Let me create a little bit of board space here. Erase this. Okay, so the end behavior is up forever on the left, right, and down forever on the right. Now don't forget which ones are bounce points. Negative 4 and positive 1 are bounce points. All right, so I'm going to bounce off of negative 4, come back up, come through negative 3, that's a cross point, and go through the y-intercept here of negative 96, and then at 1, bounce off of that x-intercept, and then turn back around. So this is the sketch of the graph. Now, here, we don't know really how low this goes, right? It can go a lot lower than negative 96. So we're unsure about this portion. We're also unsure about this portion, like how high does it go between -4 and -3? We don't know that either. Okay, so there's a lot that we don't know, which is why we're calling it a sketch. Okay, this is not an exact picture. All right, everybody. I hope you learned a lot in this lesson. Catch you later.